Okay, this is Chapter 1, Data Collection. In this chapter, in Chapter 1 just specifically, and really the first half of this class, we're going to be talking about what we do with the data that we collect. And anyways, Chapter 1 specifically has a lot of vocabulary. But in this chapter, we're going to define what statistics is and statistical thinking, explain the process of statistics, distinguish between qualitative and quantitative variables, then distinguish between discrete and continuous variables, and determine the level of measurement of a variable. Statistics is the science of collecting, organizing, summarizing, and analyzing information to draw conclusions or answer questions. In addition, statistics is about providing a measure of confidence in any conclusions. Whenever we talk about data, which I'm about to say, just so you know, it is a plural word, so sometimes it may seem like the sentence sounds weird. It's because a lot of people say data is instead of data are, but just so you know, that's why it's worded, because it's a plural word. So the information referred to the definition is data. Data are a fact or proposition used to draw a conclusion or make a decision, and we describe that as a characteristic of an individual or item. And so that's actually the things we collect. And a lot of the things that we're going to do in this class is we're going to learn how to collect data. And then once we collect data, we're going to learn how to organize the data. And so that's a lot of the things that we're going to be doing in Chapter 1. So there are a couple more terms that you need to be familiar with, and these will not go away. We'll be talking about these throughout the semester. Whenever we talk about the entire group, or what I like to consider the whole, that is called the population. And a lot of times population, whenever you're talking about population, it will also use words like all, meaning everyone, the whole of what you're talking about. So an example of population could be 5,000 Midland College students. About to write over this, sorry. So let's just say that's the whole of Midland College. So everyone that goes to Midland College, 5,000 people. And I'm going to go to sample next. Sample is a subset of the population that's being studied. So maybe we could say a part out of that whole, or again a subset, would be this statistics class. And then the individual is a person or object that's being studied. So this individual in this case could be you. You are technically a Midland College student. You're taking this stats class and you're the individual. Another example, it doesn't always have to be humans. I don't know. Another example could be the population could be dogs. And the sample could be beagles because they are a subset of actual dogs, a breed. And then maybe the individual is my dog Annie. So a parameter is a numerical study of a population. So it's a number that describes the population, and whenever you see population and parameter, they both start with P. So maybe we could just keep going off of Midland College. The percent of Midland College graduation. I'm going to say graduating. The percent of Midland College who actually end up graduating. And then the sample, a statistic is a numerical summary based on the sample. So they both start with S. And maybe our statistic is the percent of students who pass this class. because it's talking about a part out of a whole. Our part was the statistics class, and the whole was was Midland College. So I usually have examples after I kind of explain what something is. And so I suggest pausing the video and reading these and trying to figure out which one is a parameter or a statistic, because I'm just going to go straight into it. But it would definitely help all of these if you pause whenever we do stuff like this and see if you can get it right. So, A, the average score for a class of 28 students taking a calculus midterm exam was 72%. Now, I know I've been talking a lot about maybe our class being a part, a sample. But it could also be the population, depending on what you're looking at. What do you consider the whole? What do you consider everyone? And so the average score for a class of 28 students, it doesn't say, I don't like how I did that. Sorry, let me do it underneath there. It doesn't say a class of 28 students in the entire high school or whatever it may be. So this class of 28 students is our whole. That's everybody. And so since we're talking about everyone and we were given information about everyone, that's a parameter. B says in a national survey of 1,300 high school students, 32% of respondents reported that someone had bullied them. So that 1,300 is that's giving us information about everyone. But the number we were given was only about respondents, which most likely is not all 1,300 people. Maybe we only had 200 respond. So because it gives us information about a part, that's going to be a statistic, a number describing a sample. So we've got descriptive statistics, which consists of organizing and summarizing data, and it describes data through numerical studies, tables, and graphs. That's going to be the first half of our course. Really, chapters 1 through 6 deal with descriptive statistics. We will be given data, or maybe we collect data on our own, and we say, this is what we know about our class, or I can summarize it numerically, or I can put it in a table and a graph and make it look a little better. Versus inferential uses methods that take results from a sample and extend them to the population and measures the reliability. This is the second half of our course. So basically, maybe our first exam, we have a 70% pass rate. So we could take what we learned about our class and maybe extend it to Midland College as a whole. And so the inferential extends what we know about our sample to the population. Once again, if you want to pause at this point and kind of see if you can figure it out by yourself, but I'm going to keep going. The document American Attitudes About Genocide provided highlights of a nationwide poll with 1,000 participants. The survey conducted by Penn, Schoen, Berland between June 30th and July 10th revealed that 66% of respondents believe that genocide is preventable. So the question is the statement, in quotes, an inferential or descriptive statement? Because it's 66% of respondents, we took whatever people said, they responded, we got information. It's not like we're not making any inferences about the population. We're just using the information that we were given. That's going to be a descriptive statistic. It then says, based on the same information, what if the statement had been 66% of Americans believe that genocide is preventable? So the thing that changed, instead of respondents, it said of Americans. So it's extending what we learned from our survey, and it's extending it to everyone that we were talking about, our population, Americans. Because it's extending it to the population, that's going to be inferential statistics. An inferential statistic. So this is really what you can expect to be doing in this course. And I will let you read this more extensively. I'll kind of summarize it, but we're going to be identifying the research objective. So the very first thing that you need to identify is what do we care about? What are we trying to get answered? Do we want to know what Midland College graduation rate is? Do we want to know the percentage of people in Midland who get speeding tickets on average? What's the average height in Midland? I don't know. Whatever it is that you want to know, you've got to figure that out. What do you care about? So identify the research objective, and then we need to collect the data, and we're going to learn good ways to collect data in this course. There are good and bad ways. Then we're going to describe the data. So instead of having all of that raw data, which you'll learn what that is, just kind of sitting there, how can we summarize it? How can we make it pleasing to the eye? And then based on what we learned, we need to do an inference, because maybe I want to know the average height in Midland. I can't ask every single person in Midland because that's a lot of people, and that's why we inference, because we can take what we know about a sample and extend it to a population, whatever our population may be. Okay, example 3. Sorry, it's a little blurry. It says, the Gallup organization conducted a survey of 1,018 adults aged 18 and older living in the United States and asked, if you had $1,000 to spend, do you think investing it in the stock market would be a good or bad idea? Of those 1,018 adults, 46% said it would be a bad idea. The Gallup organization reported that 46% of all adults aged 18 and older living in the United States thought it would be a bad idea to invest $1,000 in the stock market with a 4% margin of error with a 95% confidence. So first off, that's a lot of information, and it wants us to answer 5 parts, but I'm just going to tell you this 4% margin of error with 95% confidence, you really don't need to know that. That's later on stuff, so we're not going to focus too much on that. I'm going to zoom in, though, so hopefully I can fit all this information on there. It says, what is the research objective? So the research objective is really the question that is being asked. So it wants to know, if you had $1,000 to spend, do you think investing it in the stock market would be a bad idea? So that's your A. What is the population? The population is all. So who do we care specifically? We care about adults aged 18 and older living in the United States. So, and honestly, anytime you do population, the word all is your friend, because it's talking about everyone, all U.S. adults 18 and older. What is the sample? Who specifically did we ask? We asked 1,018 adults aged 18 and older living in the United States. So that'll be that 1,018 number. It then says, list the descriptive statistics. So what did we learn about the sample? We learned that out of those adults, 46% said it would be a bad idea. So that 46% is your descriptive statistic. And what can be inferred about this study? Then it's basically what they concluded. And then so it says, I'm going to do this one in green. The Gallup organization reported that 46% of all adults, so that's it inferring about the population, all, aged 18 and older, living in the United States, thought it was a bad idea. So it's also 46%, but I'm going to tell you that's not always the case. It has been for the last 2 examples. And a lot of the times it's close, but it won't necessarily be the same. And we'll learn how to calculate that later on in this course. Okay, so variables. Variables are the characteristics of an individual within the population. What are individuals, though? Individuals can be whatever it is that you're talking about. Is that people, dogs, oranges, whatever it is that you're talking about? That's what the variable is. And variables vary. Consider the variable height. If variables had the same height, the notating height of one individual will be sufficient in knowing the heights of all. But that's not the case. We know that people are different heights. And so the point is, what makes the variables change? And so we're going to talk about different variables and kind of go from there. There are two types, qualitative and quantitative. They look like they're spelled the same, except one has an L and one has a T. So qualitative, which we can abbreviate using this QL, is also known as categorical variables, and it allows for classification of individuals. And so when I think of qualitative, I think of it's not a numerical value. Maybe an example of a qualitative variable would be hair color, favorite TV show. Anything that you favor is a category. And yeah, just anything that has some sort of category. Maybe your favorite candy, Starburst color, whatever that may be. Quantitative, is abbreviated with QN. And the root word of qualitative is quantity. And so you can kind of think of it like that because quantitative provides numerical measures of individuals. And they can be added or subtracted and provide meaningful adults. So maybe it's height, grade, speed, anything that has quantity that can be measured. I think of things that could be averaged together. I can't average together hair color. Well, maybe you can. I'm not a cosmetologist, but as far as I'm concerned, I don't think you can. I can't subtract hair color at least. So quantitative, again, provide numerical measures. So let's distinguish between the two. And here's some examples, and if you need to pause, go for it. Number of siblings is quantitative, and I'm going to abbreviate it with QN because it's a numerical measure. Favorite TV show, anytime you see that word favorite, it's going to be qualitative. I'm going to skip to D, and then I'm going to talk to you about C. Daily volume, that's a measure, that's quantity. Now, number on a baseball jersey, I know when you see the word number, you want to think quantitative. It's actually qualitative. And it's qualitative because being number 7, let's say your baseball jersey is number 7, doesn't mean you're the best in the world. It doesn't give any indication on your ability to play baseball. It's just a category of who you are on the baseball team. And so that is why it is qualitative. Now we have two types of quantitative. So here you've got your variables, and it's either qualitative or quantitative. If it's qualitative, you're done. But if it's quantitative, then you may be asked what type of quantitative variable it is. And there are two types. There are discrete and continuous. Discrete is a quantitative variable that has a finite number of values or countable possible values. So maybe it represents a number that is 0, 1, 2, 3, something like that. Siblings is an example. You're not going to have 2.3 siblings. That just doesn't make sense. So, and a continuous variable is a quantitative variable that has infinite number of possible values. So it can be as specific as possible, meaning maybe a speedometer is an example. It could be very specific, meaning you could be going 5.6789, miles per hour. It can be very, very, very specific. And so that's an example of a continuous variable. So we have a couple more that we can maybe identify between continuous and discrete. We know that they are all of these are quantitative. So once we know that they're quantitative, then we say, okay, is it discrete or continuous? So volume lost, and I'm going to represent continuous with a C and discrete with a D. Volume lost each day can be very specific. So that is continuous. Number of sequoia trees in a randomly selected acre. So that is actually going to be discrete. Because number of trees, you just go around and say, okay, that's 1 tree, 2 tree, 3 tree. They're going to be whole numbers. Now, if you ask the height of sequoia trees, then that would be continuous because that could be very, very specific. Internet connection speed in kilobytes per second. Now, I'm just going to tell you, if you don't know anything about internet connection, that's okay. But really, anything to do with speed is going to be a continuous variable. And number of points received on a statistics exam, I'm just going to tell you I'm going off of mine, and I do whole points, so that's going to be discrete. So data is the list of observations a variable assumes. It's called data. And so, once again, this is just kind of a summary of what we talked about, qualitative and quantitative, and the specifics that can go into each. Okay, this is section 1-2. And in this section, we're going to be talking about observational studies versus designed experiments. And we're going to distinguish between the two and explain the various types of observational studies. So we're going to have to get through some long slides, and I apologize, but we're just kind of making a point here. And I will kind of abbreviate some of this. So researchers and associates wanted to investigate cancer risk among Danish cell phone users who were followed for up to 21 years. They kept track of 420,095 people whose first cellular telephone subscription was between 1982 and 95. In 2002, they recorded the number of people out of those 420,095 people who had a brain tumor and compared it to the rate of brain tumors in this group to the rate of brain tumors in the general population. They found no significant difference in the rate of brain tumors between the two groups. They concluded that the cellular telephone was not associated with an increase for brain tumors. So all they did was just see what happened. They didn't tell the people what to do. They just said, use your cell phones like normal, and we will see what happens. So they did another study, and in this study, they examined whether the chronic exposure to radio frequency radiation at 2 common cell phone signals, which are those 835.62 megahertz and 877.74 megahertz, caused brain tumors in rats. So now rats are our variables. The rats in group 1 were exposed to an analog cell phone frequency, and in group 2 were exposed to digital frequency. Then we had a group 3 that served as a control, which meant that nothing was done to them. They just kind of did their own thing. And then we looked at that exposure for 4 hours a day, 5 days a week for 2 years. The rats in all 3 groups were treated the same except for the RF exposure. After 505 days of exposure, the researchers reported that they found no statistically significant increase in any tumor type, including brain, liver, lung, or kidney, compared to the control group. So, what does that mean? In both studies, the goal was of the research was to determine if the radio frequency was maybe causing some brain tumor. And so whether or not brain cancer was contracted is the response variable. Sorry, my pen's not working. There we go. And the level of cell phone use is the explanatory variable. And you'll see these words a lot in this class. The response variable, I like to think of as the dependent variable. And the explanatory variable I like to think of as the independent. Kind of like your X and Y if you've taken a math course before. Independent. And so we're trying, and response literally responds to explanatory. And explanatory is you're trying to explain why something would maybe respond this way. We also have observational studies and designed experiments. An observational study measures the value of a response variable, so there's that word again, without attempting to influence. So we're just kind of seeing what happens and writing down our information of either the response or explanatory variable. That is, in an observational study, the researcher observes the behavior only. We're not trying to influence the outcome. So observational study would be like the examples that we just read about, because we just we let people talk on their phones, and if they got tumors, they got tumors. We just collected the data. If a researcher assigns individuals in a study to a certain group, intentionally changes the value of the explanatory variable, and then records the value of the response variable for each group, the researcher is conducting a designed experiment. And so this designed experiment would be more of the rats, because they assign the rats to specific rooms with those radiations, and they saw what happened. So observational is we just kind of see what happens. And I mean, it's really self-explanatory because it's got the word observe in it. And then designed experiment, I think of as the researchers have more control. Of who goes to what group, and kind of more control over how the experiment is conducted. So again, here are two examples, and we're going to determine the which one is which, either observational or designed experiment. So it says in a study in which balding men were compared with non-balding men at one point in time found that balding men were 70% more likely to have heart disease. So A is observational. It's observational for a couple reasons. A, we cannot control if people are balding or not. I mean, we're just going to look and see, oh, you're bald, do you have heart disease or not? Observational studies are done all the time with stuff like this. Maybe does smoking affect if you have lung cancer or not? We can't just handpick people and ask them to smoke, because that would be unethical. It's just like this. We can't just handpick people who aren't bald in a study about balding men. So, and compare them with non-balding men, right? So you're either in one group or the other. B says 250 people are asked to perform a taste test in which they drink from two randomly placed unmarked cups and ask which drink they prefer. So this is a designed experiment, because we as the researchers, maybe we put all these cups out here. We decided what was in the cups. We decided how many people were in the study, and we went from there. So in this case, we have a little more control. There are types of variables called confounding and lurking. Confounding in a study occurs when the effects of two or more explanatory variables are not separated. So in that case, maybe we cannot figure out what caused what. And any relationship that exists between an explanatory variable and response variable may be due to some variable not accounted for. Versus lurking variable is an explanatory variable that was not considered at all in the study, but maybe still affects what we're looking at. And I'll give you an example of that in a second. But lurking variables are typically related to any explanatory variable considered in the study. So here's a study about influenza, and it says that researchers wanted to determine the long-term benefits of the influenza vaccine on seniors aged 65 years and older. The researchers looked at records of over 36,000 seniors for 10 years. The seniors were divided into two groups. Group 1 were seniors who chose to get the flu vaccination, and Group 2 were seniors who chose to not get the flu vaccination. After observing the seniors for 10 years, it was determined that the seniors who got flu shots are 27% less likely to be hospitalized for pneumonia or influenza, and 46% likely to die from pneumonia or influenza. So let's talk about that. Some lurking variables, aka things that they didn't consider, maybe that could affect whether or not you have influenza, other than if you got the shot or not, would be age, right? Age affects whether you get sick or not. The status of your health before they even did the study, they didn't think about that. Mobility of the senior. These are just a couple. You could think about a couple more, but that's what a lurking variable is. It's things that are still affecting it that we're not considering in the study. While a confounding variable, like we talked about earlier, is an explanatory variable that was considered, but we don't know maybe what is actually causing it. Maybe we have a couple variables and we didn't do a very good job of conducting the experiment. So an example of this is we plant tomatoes in a garden that's half shaded. We test a fertilizer by putting it on the plants in the sun and applying none to the shaded plants. Months later, fertilized plants bear more and better tomatoes. Well, great, but is that because we fertilized it or because it was in the sun? And so a good way of fixing problems that could arise like this are doing more examples, more trials, more groups in this case. So let's say I have 4 groups, and I'm going to try to do this the best I can. Let's do 2 groups in the sun, and I'm going to do shaded. I'm just going to do HS for half shaded. 2 groups that are half shaded. And then to figure out if it's the sun or the fertilizer, we could then do a group with fertilizer and sun, no fertilizer and sun, half shaded with fertilizer, half shaded with no fertilizer, and maybe after the experiment, if these do really well, then we know it's the sun. If just the fertilized ones do really well, then we know it's the fertilizer. So that's how we can try to control the confounding variable. We've also got different types of observational studies, kind of like we got different types of quantitative variables. So those observational studies are cross-sectional, and I'll kind of tell you what they are as I read along, but cross-sectional is observational studies that collect information about individuals at a specific point or over a very short period of time. And a lot of people like these because they're cheap and easy to do. So maybe surveys. You give someone a survey, they can usually fill it out in 5 minutes or less. Case control studies are studies that are retrospective, which means that you can look back in time to get information and compare it to what you're looking at now. And in these case control studies, individuals who have certain characteristics are matched with those who do not. A lot of hospitals do this. A lot of companies do this. Maybe what worked back then versus what's working now, or what didn't work back then, which is working now. And so you just compare to things that you're looking back in time, like it says, retrospective. And then cohort is a cohort study first identifies a group of individuals to participate, and they are called the cohort, and then they're observed over a long period of time. And over this period, you look at, you're just constantly collecting data over the cohort. And an example of that is Midland College has a med school cohort. They are called med school cohort for a reason. I'm going to put MC in parentheses for Midland College. And, I mean, they're just going to be constantly, how many people did we let in the program? Out of the people that we let in the program, what percentage got into medical school? What percent of people finished medical school? So it takes a really long time to get information about these cohorts. Okay, so example 3, get married, gain weight. Are young couples who marry or cohabitate more likely to gain weight than those who stay single? Researchers followed 8,000 men and women for 7 years. At the start of the study, none of the participants were married or living together with a romantic partner. Then they found that women who married or cohabitated during the study gained 9 pounds, and that men who cohabitated or married gained 6 pounds on average, more than single men. So we're going to answer a couple questions. Why is this an observational study? This is an observational study because you can't control who marries who. That's up to the individual. That's up to the people that you're studying. So you get to choose marital status. I'm going to write over this. I'm sorry. And what kind is it? Because it happened over such a long time, 7 years, it's going to be a cohort. What's the response variable in the study? What's the explanatory variable? So B, honestly, is all in the title. Get married, does it cause you to gain weight? Getting married is the explanatory variable. I'm going to write a little M. And gaining weight is the response variable. Does getting married cause us to gain weight? Identify some potential lurking variables. So, and I'm going to write that down here. What other things could affect weight gain other than living with someone? Maybe it is your age. Maybe it is your lifestyle, if you work out, if you don't, the way you eat. There are other things that could affect gaining weight. And another thing that you could look at is, why do women gain more weight than men on average once they get married? Maybe it's because they were bearing children at any point during that cohabitation. And D, can we conclude that getting married or cohabitating causes one to gain weight? You have to be really, really, really careful about that word causes and statistic, because you have to be certain that without a doubt this causes this. And so I'm not confident enough in this. We can't say that this definitely is the only reason that people gain weight. So I'm going to say no. Example 4, do people who order salads at fast food restaurants typically order a diet drink as well? So a local fast food restaurant asked the customers to complete a survey. Whoa, didn't mean to do that. There we go. One question asked what food item was ordered by the person completing the survey, and another asked what drink was ordered. So it says, what type is this? What type, or why is this an observational study? Because the customer chooses their food. We don't have any effect on that. We just say, what do you want? And they choose it. And then B says, what type of observational study is this? This is a cross-sectional, because we got our answers very quickly. Anytime you, for the most part, anytime you do something with surveys, it's going to be cross-sectional. All right, example 5 says, researchers wanted to assess the long-term psychological effects on children evacuated during World War II. They obtained a sample of 169 former evacuees as a control group of 43 people who were children during the war but were not evacuated. The subjects' mental states were evaluated using questionnaires. It was determined that the psychological well-being of individuals was adversely affected by the evacuation. So why is this an observational study? Because the people that we're looking at, we didn't have any control whether they were evacuees or not. So we can't control who put the kids in groups a long time ago. And so I'm just going to put, we can't control kids in groups. I'm going to put can't control World War II evacuees. And then it says, what type of observational study is this? This is a case control study because it happened over a long period of time and it was a little retrospective. It went back in time. And lastly, a census is a list of all individuals in a population along with a certain characteristic of each individual. So, census helps us learn about what's going on, what we can predict, how we can predict growth, how we can deal with growth that could be happening in a place. This is how we get demographics, how we know maybe how many women versus how many men are in an area. And so it just gives you really good information about all the individuals in a population, whether that is all the people in the United States, Texas, Midland, whatever it may be. Okay, section 1.3 is over simple random sampling, and the objectives here are to obtain a simple random sample. So first, random sampling is the process of using chance to select individuals from a population to be included in the sample. If convenience is used to obtain a sample, then the results are meaningless. We can't do the convenient thing. We have to make sure that our sampling is done well. And random sampling is a very common type of sampling. So, simple random sampling, we're going to be doing a lot of variables in this course and a lot of maybe letters that represent something. And this is really the first that you'll see. But a sample size n, lowercase n is sample size. And uppercase N is population size. As a reminder, sample size is part and population is whole. And it says is obtained through simple random sampling. Simple random sampling we can abbreviate as SRS, and you'll see that a lot as well. And if every possible sample size N has equally likely chance of occurring, then it's called a simple random sample. So what does it mean to have an equal likely chance? Well, there are good steps to obtain a simple random sample. And so we need to figure out the list of individuals in a population of interest. So how many people are we looking at? Are we looking at Midland, who has, I believe, around 200,000 people? Are we looking at Midland College, whatever that is, 1 to 5,000? And there are other ways to obtain a simple random sample, so maybe we can use a table, graphing calculator, software, and figure out a good size to get. So maybe our N is, let's say I'm talking about Midland College. We've got 5,000 people. Maybe my N is decided to be 100, which means I need to ask 100 people whatever it is that I'm going to ask. Maybe I ask them if they want a dog or if they have a dog. I don't know. That's the data I'm collecting. And it also said make sure that everyone has an equal chance. And what that means is we could use technology like the examples above because it saves time. But you really could put a lot of names in a hat and draw that way too, because that technically means that everyone had an equal chance if everyone's name was in the hat one time. So here's another example that we could do. So let's say we've got team captains, and a coach must select 2 players to serve as captains, and he wants to randomly select the captains. We've got Maddie, Brienne, Evan, Tori, Claire, Jory, and Peyton. List all the possible samples of size 2 from this population. Then describe the process the coach might use to select the team captains. So I'm going to show y'all first a good way to list all of these possibilities. And I'm going to do that by writing the girls' first letter in their name just to save room. And I'm going to zoom in a little bit. So we've got the possibilities. Maddie could be captain with Brienne. She could be captain with Evan, Tori, Claire, Jory, or Peyton. So those are all the possibilities with Maddie. And then Brienne, well, Brienne's already been a possibility with Maddie, so I'm going to start with Evan. Tori, Claire, Jory, Peyton. And then again from Evan, Tori, Claire, Jory, Peyton. Tori, Claire, Tori, Jory, Tori, Peyton. Claire, Jory, Claire, Peyton. And then Jory and Peyton could be together. So those are the ways that we could essentially look at all the possibilities. Now, how do I pick once I've laid out all those possibilities? Where there's a couple different ways you can do it. You could maybe number all of them, 1, 2, 3, so on, so on. And maybe I put all these numbers in a hat and I choose, and that's the group that gets it. Maybe I put it in a number generator. If you go to random.org, that's an example of a random number generator. But maybe I put all the numbers in a hat and I get, 8. So that means that Brienne and Evan are now the team captains. Another example is the 112th Congress of the United States had 435 members of the House of Representatives. Explain how to conduct a simple random sample of 5 members to attend. So that 5 is your sample size. We have a sample size of 5. We're choosing 5 people out of 435 members. And I believe the members have their own number already, their seat number. And so you could literally put 1 through 435 in a hat and choose them. Or you could put it in a random number generator, but maybe I put them in a hat and I get 213, so that person gets to go 144, 96, 27, 323, right? So those are my 5 seat numbers that get to go. Section 1.4 is over other ways to sample other than the simple random sample that was in 1.3. There are 3 other ways. One's called stratified, systematic, and cluster. So let's talk about stratified first. A stratified sample is obtained by separating the population into non-overlapping groups, and that is called strata, those groups. And then obtaining a simple random sample from each strata. And those individuals should be similar in some way that you group. So maybe let's talk about Midland, and let me put Midland. And I want to break them into male and female. So that would be the strata, the groups. And then let's say I'm going to choose 50 males and 50 females in my survey, whatever that survey may be. And so first you group them into groups called strata, and then randomly take some from each. So let's figure out how to do that. The owner of a private food store is concerned about employee morale. She decides to survey the managers and hourly employees. So that's your strata. One is managers, one is hourly employees, to see if she can learn about work environment and job satisfaction. From the list of workers at the store, obtain a stratified sample of 2 managers and 4 hourly employees. And so I'm going to circle these in black. The black are my strata. And once you separate them, then you can randomly select. And it doesn't have to be the same because there's only 8 managers and there's 2, 4, 6, there's 21 employees. So we're only going to choose 2 managers and 4 hourly employees. That's okay. And so how would I do that? Maybe I would number them and pick a number, right? Kind of like I did with the soccer example. And so maybe I randomly choose Carlisle and Lindsay. And then I do the same for the hourly employees. I number them 1 all the way to 21. And I randomly choose I choose 4 specifically. Maybe I get Cole, Hall, Musa, and Kemp. And we go from there. Another example, another way to get a sample is called systematic sampling. And that's obtained by selecting every kth individual from the population. And it's randomly selected. You start by selecting someone between 1 and K. And what is K? So we'll learn how to do that. But an example of this was saying, I will ask every 3rd person I see what their favorite dog is, or whatever it is. I keep using dog examples, but whatever it may be, that is the strata. The systematic example. It's every person, whether it be 3rd, 5th, or 12th, you systematically ask that every whatever it is person. So there are steps in getting that systematic sample. And those steps are: try to approximate the population size, which is our uppercase N. Determine the sample size, lowercase n. Figure out what big N divided by little n is and round down. This will be your K. This basically means that you get to spread out what you're going to ask. So maybe I'm at a party. I don't want to ask the first 10 people I see. I want to spread it out and make sure that I get the people that come to the party later and the people that come to the party earlier. So you want to spread it out. So that's how you're going to find your K. Then you randomly select a number between 1 and K, and you call this number P. I know, we're getting a lot of letters, but hopefully it'll make sense in a second. And this sample will consist of the following individuals. You can find it by using this formula. I'll kind of show you how I do it on the next slide, and we can go from there. Okay, this is dealing with big numbers, so just so you know, but the process is still the same. So it says, to predict the outcome of a county election, a newspaper obtains a list of all, so that's your N, your big N, I should say, population, size, 945,035 registered voters in a county. Using a systematic sampling process, select a sample size of 130. So our big N is that 945 number. And our little n's that sample size, 130. The first step says to divide them. If I divide these two numbers, I'm running out of room, so I've got to kind of write this over here. Big N divided by little n, I get 7,269.5. And in the directions, it said to always round down to the nearest integer. So that'll be 7,269. So I'm basically going to ask every 7,269th person I see. That's my K. And really the next part is, but where do I start? There's between 1 and 7,296 people, right? Like, where's my starting point? So that's when you select randomly a number, which I did through random.org. And I got, what did I get? Let's see. P is equal to 2,684. It has to be somewhere between 1 and that 7,000 number, right? So we know where to start. But this is basically our starting point. And then we can just add 7,269 each time. So here we go. We're going to add, I don't like that green. I'm going to start over. Okay. We start with 2,684. And then I'm going to ask the 7,269th person after that, which is, let's see, what is that? Do it on my calculator real quick. 2,684. That would be the 9,953rd person. Then I just keep going. I keep adding 7,269. 7,222. I'll do one more. Plus 7,269. Then I ask the 24,491st. And so the same thing's happening from here to here to here. I'm adding that 7,269. I'm adding that K every single time to get that next number. The last sampling method that we're going to talk about is cluster sampling, and it's obtained by selecting all individuals within a randomly selected collection or group of individuals. This is very similar to stratified, and people get them confused, but basically cluster is maybe, let's take Midland again. And this time, you pretty much do the same thing where you break them into groups. This time I'm going to break them into age groups. So 0 to 18, 18 to 30, no, 19 to 30, sorry. 31 to 60, and I don't know, 61 plus. Okay, so the difference between cluster and stratified is normally with stratified, I would take some from each of these, right? Some from here, some from here, some from here. But with cluster, you don't do that. You break them into groups and then you take an entire group. So I'm going to take everyone from 19 to 30 in Midland and ask them what their favorite candy is. I don't know. You can take one group, you can take two groups, but that just takes more time and money. It depends what you have. Example 3 says, describe how a cluster sample could be obtained to select individuals who have high cholesterol in a particular city. There's a couple different ways that you could do this. There are a lot of right answers here, but let's think about practitioners in Midland. I'm going to use Midland again. So here's Midland. And maybe, I don't know, there's more than 4 practitioners in Midland, but I've got one practitioner, another one, another one, another one. Let's just do 5 actually, because I did 4 last time. And it says we want to maybe ask them the amount of people they get with high cholesterol, who they see. And so a way that I could do a cluster sampling is I'm going to ask all of practitioner 1's patients and all of practitioner 3. So I ask, I take entire groups and ask all of them versus some from each group. Here's a visual example of the 4 that we've talked about. So Simple random, we just randomly select some from a population. Systematic, we choose every nth person, right? In this case, every third. Stratified and cluster are the ones that we will get confused a lot. A lot of people do. They start the same. We break them into groups, but then strata, we take some from each group, versus cluster, we just take entire groups and select them. So, once again, a stratified and cluster are different. In a strata, we divide the population into 2 or more groups. So we divide first, and then we obtain a simple random sample from each group. That's the main thing, each. In a cluster, we divide the population into groups. So same thing, dividing into groups. And then we take a random sample and survey all the people in selected groups. Convenient sampling is something that you need to watch out for. It's it's pretty self-explanatory. It's you sampling in a convenient way. It's usually easily obtainable. And anytime that happens, the results are not very good. And you should look at them with skepticism, and they probably won't tell you very much about the actual population that you're trying to observe. So example 4, we're going to be looking into each sampling method, including convenience, and talk about each one. So A says to determine the prevalence of HGC used among high school varsity baseball players, the UIL randomly selects 50 high schools. All members of the selected schools are tested. All members of the selected schools. So it broke them into groups and then chose entire high schools to look at. Because it's choosing entire groups, this is going to be a cluster sample method. B says 24-Hour Fitness wants to administer a satisfaction survey to its current members. Using its roster, it randomly selects 40 club members and asks them about their level of satisfaction. This is a simple random sample because it randomly selected from its members. C says a radio station asks its listeners to call in their opinion regarding the use of U.S. forces in peacekeeping missions. This is convenience. It is convenience because it must have been convenient that you were listening to the radio, and it's asking them to call in. And so you're not going to get very good information about the population as a whole, how they feel about peacekeeping missions. D says a member of Congress wishes to determine her constituency's opinion regarding estate taxes. She wishes her constituency, she divides her constituency into 3 income levels, low, middle, and upper. Once she divides them into those groups, she takes a simple random sample from each class. This is an example of a stratified sampling method. We broke them into groups and we took some from each. President Thomas wishes to know what percent of Midland College students each in the campus, I think that meant to say eat. In the campus dining hall, he has a list of 5,325 currently enrolled students and randomly selects a student from the first 53rd on the list. After that, he selects every 53rd student until 100 have been selected. Because it's every systematic student, right? Every 53rd person, we're going to call this systematic sampling. I just want you to know this exists just to make your data as legit as possible. There is something called multi-stage sampling. Again, this is just to help you get data as legit as possible to help you infer about the population. So As an example of multi-stage sampling, consider Nelson Media Research. Nelson randomly selects households and monitors the television programs these households are watching through a people meter. The meter is an electronic box placed on each TV within the household. The meter then measures what program is being watched and who's watching it. Nelson selects the households with the use of a two-stage sampling process. So this is multi-stage sampling. The first is using the census data. We divide the country into areas. Those are the strata. And they are typically city blocks in urban areas and geographic regions in rural areas. About 6,000 strata are randomly selected. Once we do that, we send representatives to those selected strata and list the households within the strata, and then they're randomly selected. So we basically had a stratified sampling method used in stage 1, and then we had a simple random sample in stage 2. Section 1.5 is over bias in sampling, and we're going to explain the sources of bias in sampling. Bias is really just people wanting you to believe something, wanting you to think a certain way. And really, this happens on social media a lot. Some people will share or submit articles that is wanting you and making you maybe sway towards a certain opinion versus another. And I guess what I would just say is anytime you read something, be skeptical and read and make sure it was done in a legit way and people aren't just making stuff up. But anyway, there are different types of bias in sampling, and so if the results of a sample are not representative of the population, then it has bias, and there are different types of bias: sampling, non-response bias, and response bias. Sampling bias means that the way that we decided to sample maybe wasn't very good. Maybe it favors one part of the population over the other. This can happen, maybe we favor gender over another, maybe ethnicity, maybe we favor age, so you have to be careful about that. And kind of hand in hand goes under coverage, and it also is a result of sampling bias. And it occurs when maybe some part of the population isn't represented. Maybe an undercoverage could be in the United States. If we are 60% female and 40% male, and then in our sample, we did 80% male and 20% female, right? That wouldn't be the same percentages. That's an undercoverage of the females that are actually in the population. Non-response bias exists when individuals selected to be in the sample do not respond to do not respond to the survey, have different opinions from those who do. Non-response can be improved through the use of callbacks or rewards. And so a lot of the time, especially with surveys, you're only going to get extreme opinions. I think about political opinions a lot. Maybe on Facebook, you see only the super left or super right opinion. You don't see a lot of middle ground people these days. And again, that can be helped with rewards and incentives. I don't know if you've ever gone to Panda Express and they give you a free entree if you fill out their survey. That's for someone like me who feels very average about Panda Express, but they're going to probably get my opinion now because I'm getting something free out of it. So, response bias exists when the answers on a survey do not reflect the true feelings of the respondent. And so an example of that could be interview error. Maybe the way that they're wording something makes you feel a certain way. So maybe they ask, don't you just love this class? Don't you just hate this class, right? The way they are wording those sentences could make you answer a certain way. Misrepresented answers. A lot of the times when you go to the doctor, people don't answer honestly if you fill out one of those forms. The wording of questions, that's similar to the interview error. If it's worded a certain way, it could make someone answer differently than they normally would. And then the order of questions or words. So maybe you start by saying, did you see what was tweeted out by Trump? And then you answer with a question that's opinionated about him. Maybe question 1 made you feel a certain way, and because of that, it made you answer a certain way for answer 2. And so those are all things that you want to avoid, because you want to get the most truthful things that people are feeling, and you don't want to mess up the data. You don't want to make it biased if you can help it. So let's look at these examples and determine the type of bias that is existing here. So the Village of Oak Lawn wishes to conduct a study regarding the income level of households within a village. The village manager selects 10 homes in the southwest corner of the village and sends an interviewer to the homes to determine household income. So this is an example of sampling bias. Sorry, I'm going to write over this. I don't have very much room. Because maybe this southwest corner doesn't give us an indication of every household income. And so the way that we could help A is maybe by doing a stratified sampling. Maybe get a sample of each corner of the village or whatever it may be. B says Midland College students are surveyed regarding their sleep habits. From a list of all MC students, a simple random sample of 100 is selected. They're asked, how much sleep do you get? This one's kind of hard. This one is going to be response bias. Because what if you had some people answer with 8? And then you asked me and I said 40. Well, that doesn't make any sense, but what are you actually asking? How much sleep do you get in a week, in a month, in a night, right? So you have to be very specific, and that could create some response bias because of how you worded that question. Lastly, an ice cream franchise is considering opening a new store in Midland. The company wants to know the percentage of Midland residents who regularly visit an ice cream shop. The market researcher obtains a list of households in Midland and randomly selects 150. She mails a questionnaire to 150 people or households, and only 4 are returned. So that's not a lot. This would be an example of non-response bias. Because we can't take what just those 4 people had and talk about it for the entire population of Midland residents. So this doesn't really refer to you. We won't be doing that in this course, but it does exist, data entry errors. It does exist, and it messes up your data. So maybe we get some data, and the data is 39, whatever we talk about, and it's entered as 93. So that's a data entry error because that's a completely different number, and now you're messing up the data. So it's really imperative, if you are inputting data, that it be checked. Always check your data. And lastly, sampling error versus non-sampling error. Non-sampling errors are errors that result from undercoverage, non-response bias, response bias, or data entry error. Such errors could also be present in a complete census of the population. So really any bias here. Versus sampling error. And it's an error that results from using a sample to estimate information about a population. This type of error occurs because a sample gives incomplete information about the population. So maybe here we collected the information right. But something went wrong at some point, and it caused an error on our part. Section 1.6 is about how we design an experiment now that we know ways to sample and things to avoid. So we're going to describe the characteristics of an experiment, explain the steps in designing an experiment, and talk about different designs. Some are called randomized design, matched pairs, and randomized block design. Okay, so lots of vocabulary here. An experiment is a controlled study conducted to determine the effect of varying one or more explanatory variables or factors. So really, factors is just another word for explanatory variables, and has a response variable. Has on a response variable. Any combination of the values of the factors is called a treatment. The experimental unit or subjects, basically what we're looking at, is a person, object, or some other well-defined item upon which a treatment is applied. And a control group serves as a baseline that can be used to compare to other treatments. And a placebo is an innocuous medication, such as a sugar tablet, that looks, tastes, and smells like an experimental medication. So let's say we want to see if medication or weight affects your cholesterol. So the medication and weight would be that explanatory variable, and that cholesterol would be response. And maybe we want to come in and say, if I give you a new med, what effect will it have? And so that new medication would be the treatment, and you would be the experimental unit because you're the one maybe in the experiment. Then we have a control group, and we say, don't take any meds. We're just going to see what happens, and you're our control group that we're going to use to compare what happens when you don't take medication. And then a placebo is a fake pill, basically. So we're going to give you a fake pill, and you're going to think that you're taking the medication to lower your cholesterol, and we're just going to see what happens. There are a couple ways that you can go about designing an experiment, and blinding is one of them, and it refers to non-disclosure of treatment. An experimental unit is receiving. There's two types. Single blind, which means that maybe you don't know if you're taking the actual medication or placebo, but I, as the researcher, would know. And then there's a double blind, which means I don't know what pill you're taking, and neither do you. And we just look at the results and go from there. And after the experiment is over, I would have to figure out who was given what. But there are times when you can't blind, and we'll talk about those as well. And this is actually one of those times that we can't blind. We can't do this experiment with blinding. And it says, a kinesiology professor is studying the effects of HIIT 30-minute workout versus a traditional 60-minute aerobic class. The professor assigns 45 participants to the HIIT class and 45 to the traditional class. The participants were instructed to only attend 3 classes per week and attend classes in their assigned category. Change in body fat percentage was recorded for each participant after 4 months. So it says, who are the experimental units? The participants, the 45 participants. What's the population? I'm going to reach a little bit here, and I'm going to say, since he's a professor, we're talking about students. So population, I'm going to say all students. That's reaching a little bit. What are the treatments? What are we doing here, right? The treatments are the class type. What's the response variable? What is this professor trying to look at? And it is the change in body fat percentage. I'm just going to put body fat percentage because I am running out of room. And why can't this experiment be done with blinding? Because you have to know what class you're going to, right? If you're in this, you will know if you're going to a 30-minute or 60-minute class. That's just not something that you can control. You can't blind this. Here's another example. A pharmaceutical company has developed an experimental drug meant to relieve symptoms associated with the common cold. The company identifies 300 adult males, 25 to 29 years old, who have the common cold and randomly divide them into two groups. Group 1 is given an experimental drug. Group 2 is given a placebo, which is the fake pill. After 1 week of treatment, the proportion that still have cold symptoms in each group are compared. What is the response variable? So what are we looking at? Do we still have cold or not? Right? Do we have it? Do we not? Do we still have symptoms, or are we good? What are the treatments? Well, we have the experimental drug and we have the placebo. And how are the factors that are not controlled dealt with? So we haven't really talked about this, but those are maybe things that we can't control that we're trying to make sure are just dealt with. Meaning maybe we put everyone who was on the back end of their cold and getting better in one group and all the people who are really, really sick in another group, right? That we don't want that to happen. We want it to kind of work itself out, and most of the time when you randomly do things, the hope is that it works itself out, and so they're dealt with through randomization. Okay, so to design an experiment means to describe the overall plan or procedure in conducting the experiment. There are a couple steps when we design an experiment. It should be explicit, aka specific, and provide direction. We need the response variable, and we also need the claim. What do you think will happen? Determine the factors is step 2 that will affect the response variable. And once they're identified, we need to determine what are going to be fixed and which can be manipulated and which we just can't control. And hopefully randomization will help us with that. Step 3 is determine the number of experimental units. The more, the better. The more, the better. As a general rule, choose as many experimental units as time and money allows. So that's just kind of a rule of thumb. You just get better data with the more people that you have, or whatever it is that you're looking for. Step 4, determine the level of the predictor variables. So control, there are 2 ways to control. You can either set the level of a factor at one value throughout the experiment or set it at various levels. The combination of the levels are all varied factors constitute the treatments in the experiment. So let's say you're looking at heart rate, and if you only look at people who have a heart rate of 60 beats per minute, then that's the only thing that you can look at. But if you vary it maybe I look at people with heart rates of 60, 50, 70, 80, then you're able to learn more and kind of broaden your experiment. And again, randomize, that is very, very, very important. It just kind of helps things work out on their own. So randomize the units to various treatments so that the effects of the variable whose level cannot be controlled is minimized. We hope that, those little things work themselves out, kind of like I said. And it's uncontrolled predictor variable. Step 5, replication. Always, always, always try to replicate if you want. The more you do an experiment, the better it becomes. And so, like it says, it occurs when each treatment is applied to more than one experimental unit. So maybe I'm looking at someone with a heart rate of 70. Well, they're not going to be able to tell me everything about people with heart rates of 70, right? I want to ask maybe 5 people with heart rates of 70 if I'm asking stuff about their cholesterol. I don't know. I just made that example. And so you don't want to just ask one person in one category or whatever your experimental unit is. It helps you make sure that the effect of a treatment is not due to some characteristic of a single person with a heart rate of 70 or whatever it is that you're looking at. Collect and process the data by measuring the value of the response variable for each replication. Any difference in value of the response variable is the result of differences in the level of treatment. And lastly, step 6 is to test the claim. This is more inferential statistics. We're trying to inference about the population. And so that's really the goal of designing an experiment, is to hopefully that we can say, okay, we learned this about a sample. Now maybe we can generalize it for the population. There are ways that we can do designs. Once we've kind of talked about all those examples, we can do something called a completely randomized design, and that's when one experimental unit is randomly selected to a treatment. So maybe you've got 100 people and you say 50 of them are getting medication, 50 of them are getting a placebo. We kind of talked about that a little bit.